Hello everyone. Today I would like to tell you about some idea which is already like 50 years old, but nevertheless lies at the very foundation of quantum theory. Namely, I would like to tell you about Cauchy-Specker theorem. Okay, so the idea is pretty simple. Let us start with like three physical properties. We know that in quantum mechanics some properties might not be measurable at the same time. So imagine that we have something like A, okay, B, and C. And right now A can be measured with B, A can be measured with C, but B and C may not be measurable at the same time. So let's go straight to the physics. So imagine a simple system for which something like that can happen. The simplest system actually is a three-level system. In this case, imagine a particle of spin 1. So let's say that observable A is spin observable along z direction but squared. So it has only two outcomes, either 1 or 0. Okay? The next one, B, must be measurable with A. So let's say that B is the same, but this time without a square. So it has three values, 1, 0, minus 1. And C, let it be Sx squared. Of course we know that Sz and Sx cannot be measured at the same time, but actually for spin 1 the cool thing is that it happens that Sz squared can be measured with Sx squared. Okay? And right now we have the following thing. Again, A can be measured with B, and A can be measured with C. And now we introduce the following idea, the idea of non-contextuality. What does it mean? Non-contextuality means that A has a value, has a well-defined value, no matter whether it's measured together with B or C. So we have actually two possible measurements, A with B and A with C. So in other words, we can choose to measure A in the context of B or in the context of C. Okay? And what does it mean that this system is like non-contextual? Or in other words, what does it mean that A does not depend on B and on C? Actually, it's not that straightforward. So maybe let me start with a different idea. What does it mean that A depends on B or C? So let's start with a simple dependence. So again, we will have this A, B, and C. So let's start with the issue of what does it mean that A may depend on B or C. So again, we have these three observables, A, B, and C, but this time A can be measured with B, A can be measured with C. So in laboratory we can evaluate probabilities like PAB and probabilities PAC. Okay, but right now we would like to observe something like dependence of A on the context of measurements. What can happen? So imagine that we measured A together with B, and then we would like to evaluate only what's the probability of A. So we simply consider this marginal, so we sum over B, and we should get something like PA. Along the same lines, if we measured A with C, and we sum over C, we obtain again the marginal P of A. But right now let me introduce some index. So this was measured with B, this was measured with C, and right now these two guys may not be equal to each other. So this is like a definite evidence that this observable A was somehow affected by the context of the measurement. So we may think that something like that may happen, but actually this would be already very unnatural, and this was shown in a very beautiful example by Perez. So you can find it in Perez's book. So imagine such a system, and imagine once more that we consider the spin 1 particle. Okay, he showed that if something like that happens, something very strange would happen in nature. So imagine that we have a beam of particles, of spin 1 particles. Okay, and now these particles come into the measurement, some measurement device that measure this observable A, which was defined as Sz squared. So we said that this observable can only have two values, either 0 or 1. And this observable 1 is doubly degenerate in the sense that this box simply cannot distinguish between +1 and -1. Okay, so this box will somehow, just like a Stern-Gerlach device, some kind of modified version of Stern-Gerlach device, will basically divide this beam into two beams, this beam, and this beam will correspond to outcome 0, and this beam will correspond to outcome 1. So right now we have a spatial separation of these beams, and we can say that this goes like, let's say, to I don't know, Andromeda galaxy, and this goes to Earth. And then what happens, due to the fact that still here we didn't say whether it's +1 or -1, we can perform another measurement. And here we simply place a detector. Okay, so let's say that here there is Alice in Andromeda galaxy, and she's measuring basically the intensity of this beam. This intensity, of course, must be proportional to this probability. So Alice hears like some amount of clicks, and then by measuring the number of clicks per minute or per second, she can estimate this probability. Okay, but on the other end, there is Bob, and right now Bob has another box, and Bob can choose whether to perform a measurement as sz. So in fact, he just gets rid of this issue that there is double degeneracy. Right now he's going to determine whether it's indeed +1 or -1. But actually he may do something tricky. He may perform a measurement of sx², which also is commeasurable with this one. So due to the fact that it's commeasurable, it should not somehow influence it, but again, imagine that it does influence it. Okay, so in this case we said that if we measure this guy together with this, we would observe completely different probability when measured together with this. But what does it mean? It means that by this choice, by making this choice, Bob can influence the intensity of the beam on the side, which is already like superluminal communication, and it's not allowed by special relativity. So we know that something like that is disallowed by some other physical principles. Okay, so this is something interesting. So we see actually that if we are looking for some kind of influence, this cannot be an obvious influence like here. So let me go to some kind of influence which would be actually contextuality, but a very subtle one. Okay, so right now I can define what do we mean by that A does not depend on the context, on whether it was measured with B or with C. It means that simply we can define the value of A independent of B and C. It exists no matter what, no matter whether we measure it with B and C, and it means that although we said that we can measure in laboratory PAB and we can measure in laboratory PAC, there exists some joint probability distribution PABC. This is a beautiful idea by Fine to show that if there is no dependence, and if the values exist prior to the measurement, then there must be at least some kind of abstract, maybe mathematical, but still there must exist some joint probability distribution from which we can derive all the measurable marginals. Okay, so right now imagine the following example. So kind of tricky experiment which was considered by Specker. So imagine that we have 3 boxes, and again we can call these boxes A, B and C, so these boxes will correspond to our observables. And what I allow is that you can look in 2 boxes at the same time. I do not allow you to look at all 3 boxes at the same time. You can only choose 2 of them. Okay? And what can you observe? So you can find that there is a ball or that there is no ball at all. Okay? You can have like different possibilities. And now it seems that it's obvious that inside these boxes, I mean, in each box there is a ball or there is no ball, and this existence of a ball inside a box does not depend on what's going on in the other box. Okay, so in this case we have like 8 possibilities, and these possibilities are the following. So plus, 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 which means ball here, ball here, ball here, or plus, plus, minus, which means ball here, and empty box here, and then plus, minus, plus. So let me erase it. Right now we know what I mean by this signs. We have plus, minus, minus. We have minus, plus, plus. We have minus, plus, minus. Minus, minus, plus. And the last one is minus, minus, minus. Okay? We have 8 possibilities and 8 exclusive possibilities. So we can assign also some probabilities to them. So this is already this assumption of non-contextuality. It means that apart from the fact that I allow you only to look inside 2 boxes, the situation with all 3 boxes is well defined. Okay? So we have 8 probabilities for 8 exclusive events, which means that the sum of all these probabilities cannot be greater than 1. Actually, let's say that these are the only possible events, so the sum of all these guys has to be equal to 1. But right now, as I told you, you can only observe what's inside 2 boxes. Okay? And due to this fact, you cannot estimate these probabilities. But what can you estimate? You can estimate, for example, the probability that there was a ball in the first box. So maybe let's write it like that. A equals to plus and B equals to minus. Situation like that can happen. We say nothing about box C. So we see that already this guy has to be equal to what? It can be realized from this situation, so plus, minus, minus, and also there might be a plus for the last box, so it's plus, minus, plus. So this guy, the sum of these 2 guys is to correspond to this guy. Okay, another situation which would be exclusive to this one is the following. So we look inside box B and inside box C. And right now, inside box B we find a ball, and in box C we find nothing. Okay? So how come such a thing like that can happen? So it can arise from this guy, so B plus, C minus, but it can also arise from this guy, B plus, C minus, and A minus. Okay? And another situation where we opened box A and box C. And now we observe that A equals to minus and C equals to plus. Okay? And you can see that this can be realized from these 2 guys, from this possibility, and also from this possibility. Okay? So now we ask, what is the sum of these 3 probabilities? What's the largest possibility? So we see that actually the sum of these 3 probabilities is actually the sum of the 6 probabilities. But since all 8 probabilities sum up to 1, we know that if we get rid of this guy, and these 2 guys are definitely not negative, this sum has to be bounded by 1. But right now imagine the following situation. So imagine that, again, we have these 3 boxes, and imagine that if you choose any 2 of them, you will always find a ball in at least in one of them. Okay? So if you choose this box, you will find a ball here or ball here, but you will never find a situation where you have nothing here and nothing here, or ball here and ball here. There will be always exactly 1 ball, and with probability 1/2 here and probability 1/2 here. If you choose this box, you will find either situation ball here, nothing here, or ball here, nothing here, again with probability 1/2, 1/2, the same for these two boxes. But what does it mean? That this is 1/2, this is 1/2, and this is 1/2, and we already violated this inequality. Okay, but again, look that this does not violate this assumption which was considered by Perez. Namely, with this we cannot violate non-signaling, simply because the probability of A does not depend on whether we measure it with B or we measure it with C. The probability of A, of finding a ball inside box A, is always 1/2. Anywhere. The probability, for every box, the probability that there is a ball is always 1/2, and the probability that there is nothing, there is vacuum, is also 1/2. Okay, so this is like the simplest example of this non-trivial influence for which we cannot find this joint probability distribution. But unfortunately, something like that cannot happen in a real world. So something like that cannot be realized in quantum mechanics. What can be realized in quantum mechanics is a slightly bit different situation. We need simply more boxes. We need 5 boxes, or we can realize it with a spin 1 particle. So imagine right now that we will have 5 observables. A, which can be measured with B, B, that can be measured with C, but A and C cannot be measured at the same time. Then D, so C can be measured with D, E can be measured with D, and A can be measured with E. So we see that each of these observables can be measured in 2 contexts, either the one to the right or the one to the left. Okay, and right now, assumed also the following thing, that either we find okay, consider that these observables are binary observables, that these are simply events. So each of these can be either equal to 1 or 0. Okay, and moreover, by this connection we will mean that these observables, these events, are exclusive. So if we observe that this happens, that this is 1, this has to be equal to 0, or if we measure this with this would be 0. Okay? How to realize it on physical system? So again, as I told you, we go to spin 1 particle. And the very interesting thing about spin 1 particle is that if you look, for example, if you measure spin along some axis n, okay, we know that we can find 3 values, 1, 0, -1. They correspond to some special states, and we can represent these states in the following way, that we simply know that projection of total spin on n axis is either 1, 0, or -1, and it can be graphically represented in the following way. So we have a spin due to the uncertainty principle. If we know the projection along n axis, we do not know what's the projection along any axis that is orthogonal to n. That is why we need to have this kind of cone, and the spin is somehow uncertain where exactly it lies on this cone. Okay, so this corresponds to +1. Then we have another state corresponding to 0, and we have another state corresponding to -1. And right now the very interesting thing is that if you choose the Sn observable, and so basically like a state, projection on state Sn equal to 0, and you take another state Sn orthogonal, so along some orthogonal axis to n, and also the corresponding state. So as I was saying, the interesting thing about spin 1 is that if you take a spin projection operator along some axis n, you will find 3 states corresponding to +1, 0, and -1. And then if you take this state with 0 projection along n axis, and you take another state with also 0 projection along some axis which is orthogonal to n, you will find that these 2 states are orthogonal. So basically, if you calculate their overlap, you will find it is equal to 0. Okay, And now you can play a little bit with geometry. So we need to find the following situation, because you know that the orthogonality of two vectors in Hilbert space corresponds exactly to two exclusive events, and as we showed here in this diagram, we need 5 cyclically exclusive events. So let's start with the following thing. So we take the z-axis, okay? So we can measure spin along z-axis, like we can measure this spin 0, this projection, the 0 projection state onto the z-axis. But actually that's not what's interesting us. We are going to define a cone which is tilted to z-axis, or basically the dilation angle with respect to the z-axis is here alpha. So you can imagine that it's in 3-dimensional space. This cone looks like that. If you choose the angle alpha properly, actually if you choose the angle alpha such that cosine alpha is equal to 1 over square root of 5, you will find that on this circle you can find 5 points, like equally distributed. So you basically take this whole angle to pi and divide this angle by 5, so 2 pi by 5, and then you just draw 5 vectors pointing from the beginning, from the origin to these 5 points. So vector number 1, let's call it vector A, vector number 2, okay, I'm not going to call it B for a moment, you will see why, vector number 3, vector number 4, and vector number 5. So you see it's something like kind of umbrella shape. And now the cool thing is, due to the fact that we chose this proper dilation angle, you will find that this vector here, A, is orthogonal to this one and to this one. So it's orthogonal to B. This one is orthogonal to this one, so let's call it C. This one is orthogonal to this one, let's call it D. This one is orthogonal to this one, let's call it A. And as I said, again, this one is orthogonal to this one. Okay, so we have like 5 directions which are cyclically orthogonal. So right now, if we define these directions as directions for which we will look for spin projection, and spin projection with the projection equal to 0, we can find 5 states. 5 states having this property that we are looking for. So 5 states which are going to be orthogonal. This to this, this to that, this to that, this to that. Let's call this state simply as state A, state B, state C, state D, and state E. Okay? This is something that can be measured in laboratory. And actually, such a thing was done already in laboratory, but actually not on spin 1, but on some other 3-level quantum system. Okay, so we know how to physically find it, we know how to construct it, and right now let us look at properties of this system. So again, we have an assumption of non-contextuality. It seems it's like a reasonable assumption in nature. And right now we are trying to find, again as before, with this three boxes, this unphysical example, but nevertheless we managed to find some kind of inequality, and we showed that there might be some non-classical effect that violates it. And still it's not like this signaling effect. Okay, so this is the subtle effect of contextuality. Okay, so we are looking for some inequality. How to find this inequality based on non-contextuality assumptions. So again, let me draw it. And then we know that we have 5 exclusive events. Okay, and now we are trying to find the following thing. What is this? We are looking at the sum of probabilities: P of A plus P of B plus P of C plus P of D and plus P of E. So what are these probabilities? So actually, look, imagine that one of these events happened. So we assigned to one of these nodes 1. What does it mean? That due to this exclusivity property, the neighbors of this guy have to be 0. Okay? Then we need to define some values on these two guys, but we know that they are neighbors. So we can assign one to at most one guy, either here or here. So let's say it's here. Okay? And then you can check all possibilities. You immediately see that you can assign one to at most 2 positions, 2 events. This means that the sum of these probabilities can be at most 2. So this is bounded by 2. Okay? But right now let us go back to these 5 states. As I told you, we can prepare them in the laboratory. And what if our state, initial state, was this SZ? So as you remember, I wrote this kind of umbrella. This was Z, and then 5 vectors on this umbrella. Okay, something like that. And then we choose state corresponding to SZ equal to 0, so a 0 projection along the axis. And right now we are looking for the probabilities here. So the probabilities actually, so sorry, I was wrong. This axis here was such that cosine square alpha has to be equal to 1 over square root of 5. So cosine squared alpha has to be equal 1 over square root of 5, not cosine alpha. Okay. So right now, due to this fact, you can observe that the probability of PA is given by simply A times psi, where psi is our state, so this is our psi. Okay? So it's this and modulus squared. Okay, so let me get rid of all these things. And the probability of B is equal to the same. Probability of C is equal to the same because of the symmetry, of this umbrella symmetry. Probability of D and probability of E. All probabilities are equal to the same value, so let's call it simply P. So we see that the sum of these guys is simply 5 times PA. And we know that it should be bounded by 2. Okay. However, due to what I showed you here, you will find that this is equal exactly to 1 over square root of 5. Which means that 5 times this probability gives you square root of 5. This is supposed to be bounded by 2, but it's already wrong since this is approximately something like 2.23, as I remember. So what we did, we just violated this inequality. So this is basically proof that you have contextual behavior in the real world, namely quantum mechanical systems allow for contextuality. Thank you.